Assalamualaikum everyone. Today our group will present our artificial intelligence project titled Campus Route Navigation System using Search Algorithm. This project focuses on how AI search algorithm can solve pathfinding problem in a campus environment. The objective of this project is to find the best route from the library, which is the initial state, to the main hall, which is the goal state, and the campus contains several connected buildings and some blocked roads that cannot be used. Therefore, search algorithms are applied to explore and determine the valid path to the destination.
Hi, my name is Akma. I will present about problem description. This project focuses on solving a campus road navigation problem using artificial intelligence search algorithms. In this scenario, an agent starts from the library and needs to find the optimal path to the main hall. The campus environment is represented as a graph where buildings act as nodes and roads act as edges. There are 9 buildings in total and some roads are blocked, which limits the possible routes available for navigation. The agent is only allowed to move to adjacent connected buildings through unblocked roads. To solve this problem, we implemented 4 search algorithms, which are BFS, DFS, Query-Based First Search, and A-star search. These algorithms are then compared based on several criteria such as path optimality, nodes expanded, time efficiency, memory usage, and heuristic effectiveness to determine which algorithm performs best in finding the optimal route.
In problem formulation, the initial state for this problem is the library, which is the starting point. The goal state is main hall, which is the destination. And for the state representation, the campus environment is represented as the graph where each building acts as a node and each valid road acts as a edge or connection. The blocked connection in this problem are admin to student center, lab to lecture hall to main hall, and cafeteria to hostel. After removing the blocked roads, the best valid path is library to cafeteria to student center to mosque and to main hall. Since each movement costs 1, the total path is 4. The operators or actions allowed in this problem are moving up, down, left or right through connected and unblocked roads. Lastly, this slide shows the state space representation diagram where the library acts as a root node and the cafeteria branch leads to the goal state while the admin branch leads to a dead end because of blocked roads. Thank you.
Next, I will explain the implementation of the 4 search algorithms. All algorithms were implemented in Python where buildings were represented as nodes and valid roads were represented as edges. Blocked roads were excluded from the graph to ensure only valid paths were explored. The first algorithm is first search or BFS. BFS explores nodes level by level using a first in, first out queue. Starting from the library, the algorithm expanded neighboring nodes until it reached the main hall. BFS successfully found the valid path, but it expanded all 9 nodes, making it less efficient because it explores many unnecessary nodes. The second algorithm is the first search or DFS. DFS explores one branch deeply before backtracking using a last in, first out stack. In our implementation, DFS first explored the admin and lab branches, but this path led to dead ends due to blocked routes. The algorithm then backtracked and continued searching until it reached the main hole. DFS uses less memory than BFS, but it does not guarantee the shortest path. Next is greedy-based first search. This algorithm uses a heuristic function to estimate which node is closest to the goal. Nodes with lower heuristic values are prioritized during traversal. Because of this heuristic guidance, greedy search expanded fewer nodes compared to BFS and DFS, resulting in faster search performance. However, it does not always guarantee the optimal path because it ignores actual path cost. Lastly, A-star search combines both actual path cost and heuristic estimation using the formula Fn equal to Gn plus Hn. This allows A star to balance efficiency and accuracy. In our project, A star successfully found the optimal route while expanding fewer nodes compared to uninformed algorithms. Overall, all four algorithms found the same valid path from the library to the main hall with a total cost of 14, but A star showed the best overall performance due to its efficient and optimal search strategy.
Next, I will explain about the heuristic design used in our campus route navigation system. Our problem starts at the library and the goal is to reach the main hall. The heuristic function we use is the estimated distance from the current building to the main hall. A lower heuristic value means the building is closer to the goal. For example, main hall has a value of 0 because it is the destination, while lecture hall has a value of 1, meaning it is very close to the main hall. This heuristic is suitable because it guides informed search algorithms such as greedy best first search and A search toward the goal more efficiently. Instead of exploring all possible paths, the algorithm prioritizes buildings with smaller heuristic values. The heuristic is also admissible, which means it never overestimates the actual shortest distance to the main hall. It is consistent because the heuristic values decrease gradually as we move closer to the goal. For A search, the evaluation function is f of n equals g of n plus hash of n, where g of n is the actual cost from the start and hash of n is the estimated cost to the goal. This allows A search to find the shortest path efficiently. Next, I will explain about the complexity analysis of the four search algorithms. We use three parameters, which is B, D, and N. B is the branching factor, D is the depth of the shallowest solution, and M is the maximum depth of the search tree. For breadth first search, the time and space complexity are both 0 to 0 of B to the power of D. BFS guarantees the shortest path, but it requires a large amount of memory. For depth first search, the time complexity is 0 of B to the power of M, and the space complexity is 0 of B times M. DFS use less memory, but it does not guarantee the shortest path. For greedy best first search, both time and space complexity are 0 of B to the power of M in the worst case. It is usually faster, but it may not find the optimal solution. For A search, the time and space complexity are 0 of B to the power of D. A guarantees the optimal path when the heuristic is admissible. Based on our analysis, A search is the best algorithm for this project because it combines efficiency and optimality. It finds the shortest route to the main hall while reducing unnecessary node exploration.
I am Fadila. I present about optimization technique. This project uses a technique to make it look better, which is called the improved heuristic. This technique is used in some search algorithms like greedy best first search and A search. The improved heuristic technique has a function that helps the algorithm figure out how close it is to the main goal. The improved heuristic enhance algorithm performance in several ways. First, reduce unnecessary node exploration. This helps the algorithm avoid unnecessary node. The algorithm chooses nodes that are closer to the goal. Second is faster search execution. This gives the direction to the search process. The algorithm searches faster because it's focused to the correct path instead of exploring all paths like DFS or EFS. Third, reduce memory usage. This reduces the number of explorers nodes. This means less memory is needed during the search process. And the fourth, better decision making. This algorithm chooses with smaller heuristic value because they are more likely to reach the goal faster. And then the last one is find the best path faster. It helps reach the optimal path faster. This helps the algorithm find the shortest quickly.
Based on the comparison result, all four algorithms successfully found a valid path from the library to the main hole with the same total cost of 14. However, each algorithm showed different performance in terms of efficiency and node exploration. Number 1, BFS guaranteed the optimal solution because it explored the graph level by level. However, BFS expanded many unnecessary nodes and used high memory. Number 2, DFS require lower memory usage because it explores one branch deeply before backtracking. However, DFS may enter dead-end path and does not guarantee the optimal solution. Number 3, greedy best first search perform faster because it used heuristic values to guide the search toward the goal. However, it only depends on heuristic estimation and may not always produce the optimal path. Okay, among all algorithms, number 4, if star search shows the best overall performance because it combines actual past cost and heuristic estimation using the function fn equal to gn plus hn. Okay, therefore, A star search was able to find the optimal path efficiently while reducing unnecessary exploration. In conclusion, this project successfully demonstrated the use of artificial intelligence search algorithm in solving a campus route navigation problem. All algorithms were able to find a valid route from the library to the main hall, but informed search algorithm perform more efficiently compared to uninformed search algorithm. Okay. The heuristic function helps improve search performance by reducing unnecessary node exploration and guiding the algorithm toward the goal state. Overall, A-star search produced the best performance because it provided both optimal and efficient pathfinding.
This is our Python code for the campus road navigation system. This section shows the campus graph representation using an adjacency list. Each building is represented as a node, while roads are represented as weight edges. Block roads are excluded from the graph to ensure the algorithms only traverse valid paths. This section contains the heuristic values used by greedy best first search and A-star search. The heuristic estimates the distance from each building to the main hall. Lower heuristic and values indicate nodes that are closer to the goal. This is the BFS implementation. BFS uses a first-in, first-out queue to explore nodes level by level. The visited set prevents revisiting nodes, while the parent dictionary is used to reconstruct the final path. BFS uses a stack structure and explores one branch deeply before backtracking whenever a dead end is encountered. Greedy search prioritizes nodes with the lowest heuristic value, while A-star search combines both actual path, cost, and heuristic estimation using the evaluation function. Finally, the program displays the comparison table showing the path found, total cost, and nodes expanded for each algorithm. Now we will run the program. We open command prompt and type python campus.py. This is BFS. It explores level by level using a queue. You can see it visits library first, then admin, and cafeteria at the same level, then goes deeper. It expanded 9 nodes and found the path, which is library, cafeteria, student center, most main hall, with total cost 14. This is DFS. It goes deep first using a stack. Notice it went into admin and left first before backtracking because the road is blocked. It also found the same path but explored in a different order. Also 9 nodes expanded. This is greedy best first search. It uses a heuristic value hn to estimate distance to the goal. You can see the hn values beside each node visited. It only expanded 8 nodes, more efficient because it uses heuristic guidance. However, it does not guarantee the optimal path in all cases. Then this is A-star search, the best algorithm.
with users have Fn equal to Gn plus Hn, combining actual cost and heuristic estimate. You can see all three values printed for each node. It also expanded 8 nodes like greedy, but unlike greedy, A star guarantees the optimal path because our heuristic is admissible. It never overestimates the true cost. At the bottom, we have a summary table. All four algorithms found the same path with cost 14. BFS and DFS expanded 9 nodes, while Greedy and A star only expanded 8. We conclude that A star is the best algorithm for this problem because it is both optimal and efficient. That's all from our group. Thank you.